the sheer volume of data we're generating globally is, well, it's just staggering.
It really is.
We're apparently hurtling towards something like 181 zettabytes by the end of 2025.
Yeah, it's a number so big it almost doesn't mean anything, does it?
Right. And a huge chunk of that, we're told, is being driven by, well, artificial intelligence.
Absolutely. The demands of AI are just insatiable for data.
And that's really the core insight here, isn't it? This
Yeah.
isn't just about more data. It's pushing how we capture it, how we manage it, how we actually use it. And, well, that's our mission for this deep dive. We're going into the world of data storage.
But not just staying here on Earth, right? We're linking it up to space exploration, too.
Exactly. We want to see how these fundamental storage ideas connect out there to the new frontiers, the exciting stuff, the complex stuff, maybe even the controversial stuff happening in space.
It really is a whole new dimension for data challenges.
Totally. So first, we'll build the foundation, look at the core storage tech, the management techniques, the basics here on the ground.
Makes sense. Got to start somewhere.
Then we'll connect all that to, well, our cosmic ambitions. We've pulled together a lot of sources for this: storage trends, system development stuff, and the whole space economy picture.
Sounds good. Let's dive in. Where do we start on Earth?
Okay, so to really get a handle on this data explosion, even how it impacts things in orbit, we need to understand the backbone here first, the core data storage tech.
Yeah.
And you mentioned the need for high-performance storage. But what's interesting is it's often not one tech versus another, is it? They often work together.
That's a really key point. They complement each other. Each one has its role. Like, take hard disk drives, HDDs.
Yeah, some people might think they're kind of old news with SSDs around.
They're absolutely not. They're still the capacity king. Unbeatable on cost per terabyte for storing massive amounts.
So definitely not fading away.
Not at all. In fact, you've got innovations like AMR, that's heat-assisted magnetic recording, and MAMR, microwave-assisted magnetic recording. They're pushing the density, how much data you can cram onto a disk, even higher.
Which makes that mass cold storage even cheaper, right? Which is crucial for things like AI training data.
Exactly. It changes the economics of handling those petabytes of data.
So capacity-wise, what are we seeing now? Like common sizes?
Well, drives around 24, maybe 32 terabytes are pretty common now.
Wow.
But we're looking at projections hitting 40, maybe even 50 terabytes or more pretty soon.
50 terabytes?
Yeah.
On a single drive. That's incredible.
It really is. And they're getting faster, too, relatively speaking. Things like dual actuator tech boost the throughput, maybe up to around 550 megabytes per second on some models.
Still not SSD speed, obviously.
Oh, no, not even close, but much better than older HDDs. And interface-wise, mostly SATA, but for really demanding stuff like those AI data pipelines, we're starting to see NVMe being adopted even for high-capacity HDDs, just helps shovel data in and out faster.
That's interesting. NVMe for hard drives.
Yeah, it's evolving. So HDDs are still vital for mass cold storage, backups, archives, the data center backbone for nearline data. And, external HDDs are still everywhere for personal use.
Okay, so if HDDs are the capacity kings, socket speed, solid-state drives, SSDs, that's where the performance is.
Absolutely. SSDs are the speed demons, and the magic ingredient there is NVMe, non-volatile memory express.
Right.
Think of it like a superhighway built just for flash memory. It lets data fly compared to older interfaces.
And the PCIe connection they use keeps getting faster, too. PCIe 4.0 is pretty standard now, hitting, 7,000 megabytes per second read?
Yeah, around 7 gigabytes a second read speed, which is already fast.
But it's not stopping there.
Nope. PCIe 5.0 is rolling out now, pushing over 14,000 megabytes per second, and Gen 6 is on the roadmap faster still, and more power efficient too.
We hear about different cell types too, SLC, MLC, TLC, QLC. Beyond just bits per cell, what's the practical difference for someone choosing a drive?
Well, yeah, the bits per cell impacts density and cost, so consumer drives use TLC or QLC mostly. But for pros, the real difference is endurance and sustained write performance under heavy load.
Okay. Lifespan and how fast it stays fast.
Exactly. An SLC drive costs a lot more, but for really demanding constant write tasks, its speed and durability are unmatched. TLC and QLC offer that balance for everyday use.
And the big capacity jump came from 3D NAND, right? Stacking cells.
That was the breakthrough. Instead of just shrinking cells on a 2D plane, they figured out how to stack them vertically, like building skyscrapers instead of suburbs.
Nice analogy.
It just massively increased density, improved performance, and lowered power use, all without making the drive physically bigger.
And that's how we get consumer SSDs hitting, what, 48 terabytes now?
Yep, and enterprise drives over 60 terabytes, maybe doubling again by mid-2025.
So SSDs win on speed, latency, throughput. And durability too, right?
Yeah.
No moving parts.
Less mechanical failure, less power draw, less space needed. Great for operating systems, apps, games. Often paired with HDDs and hybrid setups.
Okay, so that covers the hardware in the box. But the really massive shift has been moving away from physical hardware into the cloud.
Oh, absolutely. Cloud storage has been revolutionary.
It's democratized access to huge infrastructure, hasn't it? Agility, scaling, without buying racks of servers.
Totally changed the game. It's not just remote storage anymore. It's this flexible, scalable resource.
And the trends now are things like hybrid cloud, multi-cloud. That's pretty standard.
Plus, distributed cloud, edge computing, pushing processing out, serverless, cloud, disaster recovery, AI integration, and even a focus on sustainability is growing.
So the big players everyone knows are AWS, Azure, Google Cloud.
Right. AWS, Microsoft Azure, and GCP. They're basically the architects of a huge part of the digital economy now.
And the innovation they drive means even small companies can access massive compute power.
Power that would have cost a fortune just a decade ago. It really has leveled the playing field in some ways.
And they offer different storage types within the cloud, right?
Yeah, that's key. You've got object storage, super scalable, great for unstructured stuff like media, backups.
Okay.
File storage, which is more like your traditional network drive, hierarchical folders.
Right.
And block storage, which gives you raw disk volumes for high performance things like databases.
And the big concerns for businesses are always cost and security.
Cost is usually pay as you go, which is flexible, but security.
Yeah, that's absolutely critical. Strong encryption, managing who has access, IAM, secure protocols like TLS, multi-factor authentication.
Plus staying compliant with regulations.
Non-negotiable.
And sometimes you still need something physical, right? External drives are still popular.
Definitely. The market's growing, especially for external SSDs now, because they're so much faster and more reliable than the old spinning external drives.
What kind of speeds are we talking there with common connections?
Well, USB 3.2 Gen 2x2 can get you up to maybe 2,000 megabytes per second.
Pretty decent. Yeah. But Thunderbolt is where the real speed is for external drives. Thunderbolt 3 and 4 are 40 gigabits per second, so around 5,000 megabytes per second actual throughput.
Right.
And Thunderbolt 5 is coming, promising over 6,000. Great for video editing on the go, fast backups, moving large files.
Okay, so we have all these drives, internal, external, cloud. But how do we make multiple drives work together reliably? That brings us to RAID.
Yep. Redundant array of independent disks, fundamental for combining multiple drives for better performance or reliability, or sometimes both.
We know the basics. RAID 0 for speed but risky, RAID 1 for simple mirroring. But what about RAID 5 versus RAID 6? That's a common server choice. What's the practical difference beyond just 1 versus 2 drive failures?
That's a really important practical question. RAID 5 uses parity. It can handle 1 drive failing. RAID 6 uses 2 parity blocks, so it can survive 2 drives failing simultaneously.
And that matters more now with huge drives.
Exactly. Rebuilding a massive drive takes a long time. Hours, maybe days. During that rebuild, your array is vulnerable. If a second drive fails while rebuilding a RAID 5, you lose everything.
Ouch.
So, with today's multi-terabyte drives, that risk window is much larger. RAID 6 gives you significantly better protection against that double failure scenario, often worth the slight capacity hit.
Makes sense. And then there's RAID 10.
Right, RAID 10 or 1+0. It combines mirroring and striping, so you get great speed and great redundancy, often used for databases, critical applications where you need both.
But no matter how good your RAID is, you still need backups.
Absolutely non-negotiable. It's the cornerstone, your ultimate safety net.
What are the main ways people do backups?
You have full backups, obviously. Then differential, that backs up everything changed since the last full backup.
Okay.
And incremental, which backs up only what's changed since the last backup of any kind.
Got it. Smaller, faster backups, usually.
Right. There's also immutable backups, really important now with ransomware. They're designed so they can't be altered or deleted once written.
Clever.
And mirroring, which is like a real-time copy, often software-based.
And that famous 3-2-1 rule.
Still the gold standard guideline. Keep at least 3 copies of your data, store them on 2 different types of media, and keep one copy offsite. Simple, effective.
And software like Acronis helps manage this. It all ties into disaster recovery planning, defining your RTO.
Recovery time objective, how fast you need to be back up after things go wrong.
And RPO.
Recovery point objective, how much data measured in time you can afford to lose. Minutes, hours, a day. These aren't tech decisions, they're business decisions.
Okay, great foundation on the tech. Now let's talk about actually using it well in, say, system development. Mastering your digital domain. Because just having storage isn't enough, right?
Yeah.
How you organize it matters.
It's fundamental. Impacts data integrity, security, performance, long-term maintenance, everything. Bad storage strategy means you're building on sand.
So where do you start? Just basic organization.
Pretty much. Disciplined file naming conventions. Sounds simple, but it's crucial. Descriptive names, project, data type, date, version. Avoid spaces, use underscores or hyphens, be consistent.
Consistency is key, yeah.
And logical file classification, group files sensibly by project stage, module, data type, maybe sensitivity level. Create folder structures that actually make sense for the workflow.
It makes finding things later much easier.
And secure sensitive stuff better. Plus, metadata, data about your data, who made it, what's in it, permissions, creation time, essential context.
Right, so you understand the data, not just find the file.
Exactly. And for the data itself, especially if it's tabular, structure it well. Break down big tables, avoid redundancy, think relational databases, unique keys.
And keep raw data separate.
Critically important. Keep the original raw data untouched. Do all your analysis and modifications using scripts, saving the results separately. That ensures you can always trace your steps, reproduce your results. Vital for science, audits, everything.
Makes sense. Reproducibility is huge. Okay, beyond organization, what about efficiency and security? Compression seems obvious for saving space?
It definitely saves space, speeds transfers, lowers costs, makes backups more efficient, but it's not free.
Uses CPU cycles, right? Takes time.
Exactly. Compression and decompression take processing power and time. Not ideal for real-time systems where latency matters, and you have to choose the right type.
Lossless versus lossy.
Right. Lossless, like ZIP, gZIP, PNG for images, gives you back exactly what you put in. Essential for code, documents, scientific data. You can't lose a single bit.
Absolutely.
Lossy compression, JPEG, MP3, MP4 throws away some data, stuff humans hopefully won't notice, to get much higher compression. Fine for media, terrible for anything else.
And encryption today feels more critical than ever.
It's vital. Protects sensitive data, whether it's just sitting on a drive at rest or moving across a network in transit. Helps with confidentiality, integrity, availability, and meeting compliance rules.
What are the main types?
Broadly, symmetric, like AES. Same key locks and unlocks. It's fast, good for encrypting lots of data. Then asymmetric, like RSA. Uses a key pair, public key to encrypt, private key to decrypt. Slower, but essential for secure communication, digital signatures.
And hashing is different again. Not for secrecy.
Correct. Hashing, like SHA-256, creates a unique fingerprint of the data. Its job is integrity checking. Change one bit, the hash changes completely, so you know if data's been tampered with.
So best practices for encryption.
Know what you need to protect. Use strong current standards, AES-256, TLS 1.3. Manage your keys very securely, often the weakest link. Use strong access controls, encrypt data in transit, and train your people. Human error is a huge factor.
Okay, data stored, data secured. How do we ensure it stays good over time? Storage validation.
Yeah, you need ways to check that the data hasn't degraded or been corrupted. There are physical checks.
Like checking the drive health itself. Smart status.
Exactly. And drives use error correction codes, ECC, internally to fix small errors automatically, but you also need logical checks.
Checking the data content.
Right. Is the information itself still correct? Consistent across systems? Are unique IDs still unique? Making sure the data remains trustworthy?
And this loops back to that disaster recovery plan we talked about.
It's the big picture. DRP isn't just backups, it's the whole strategy to recover after any disruption, power outage, cyber attack, fire, flood.
What goes into a good DRP?
You need a risk assessment, what could go wrong? A business impact analysis, BIA, what's critical, what's the impact if it fails? Your backup recovery plan, continuity plans, communication strategy, and testing. You have to test it regularly.
A plan you don't test is just paper.
Exactly. And that 3-2-1 backup rule is still a core part of the data recovery piece.
And lastly, long-term management. Backup versus archiving. They're different, right?
Yes, very different goals. Backup is for recovery, getting back data you lost recently. Archiving is for retention, keeping data long-term, often for legal, compliance, or historical reasons. It needs to be accessible, but not necessarily instantly recoverable.
And that means having policies.
Absolutely. Clear data retention policies. How long do you keep different types of data? And disposal policies. How do you securely get rid of it when it's no longer needed? You can't just keep everything forever.
Fantastic groundwork. Okay, let's shift our gaze upwards now.
Mm.
Beyond the horizon, the space industry and this idea of new ground computing, this is where data storage gets really interesting.
It does. The scale and complexity just jump to another level. First off, the space economy itself is huge and growing fast, valued around $400 billion in 2023.
$400 billion, wow.
And something like 71% of that was satellite-related. It's driven by tech advances, lower launch costs. We're in what they call New Space 2.0, much more commercial.
So not just NASA and government agencies anymore.
No way. Private companies are massive players now, and even smaller countries are getting involved, like Taiwan wanting to build satellites. Access is widening.
How do people usually break down this space ecosystem? You mentioned upstream, midstream, downstream.
Yeah, that's a useful way to think about it. Upstream is the R&D, building the rockets, the satellites, GSO, MEO, LEO, the ground equipment. The hardware, basically.
Okay.
Midstream is the services launching the satellites, managing space traffic, which is a huge growing issue, operating the satellite networks.
Getting them up there and keeping them running safely.
Precisely. And downstream is where most of the money is currently made. It's the applications using those space assets. SATCOMs, GPS navigation, Earth observation, weather, farming, traffic monitoring. Even direct mobile-to-satellite comms are emerging now.
And tying a lot of the data side together is this concept you mentioned, new ground computing. What's that about?
It's essentially the really tight integration between space tech, mostly satellites, and ground tech, specifically cloud and edge computing.
You're bridging space and Earth for data processing.
Exactly. The goal is better efficiency, lower latency, enabling real-time analysis. It's key for things like next-gen space internet and actually making sense of the flood of data as it's collected, not days later.
So processing data closer to where it's gathered, even in orbit.
That's the edge computing part. On orbit, pre-processing. Satellites with powerful onboard computers, often using AI, can analyze raw data right there, identify ships, detect floods, filter out cloudy images. Then they compress it and send down just the valuable insights, saving massive amounts of bandwidth.
Like the Mars rover figuring out which rocks are interesting enough to send pictures of.
Perfect example. NASA uses AI edge computing on the rover to do exactly that, saves critical time and bandwidth over that huge distance.
And the cloud on Earth handles the really big stuff.
Yeah, the cloud does the heavy lifting, processing huge archives of high-res satellite imagery, running complex global climate models, distributing data worldwide. Services like AWS and Azure make satellite data much more accessible.
And AI and machine learning are just woven through all of this now.
Oh, completely. AML is revolutionizing how we analyze satellite images, detecting deforestation, crop health, glacier melt, way faster and often better than humans.
Pattern recognition at scale.
Exactly. Powering disaster warning systems by analyzing weather and seismic data, optimizing satellite operations, adjusting orbits, avoiding collisions. Google uses AI heavily for environmental monitoring with satellite data.
And these low Earth orbit LEO satellite networks like Starlink, they're fundamental to this new infrastructure.
Absolutely foundational. LEO sats are key for global internet coverage, especially remote areas. Also for remote monitoring, IoT, military comms. The big advantage is low latency.
Because they're closer, right?
Much closer. 500 to 2,000 kilometers up versus 36,000 kilometers for geostationary satellites. That proximity makes a huge difference for anything real-time.
So give us some real-world examples. How does this new ground computing actually touch our lives?
Well, smart cities use it. Traffic management fusing satellite and ground sensor data, environmental monitoring air quality, urban heat islands, infrastructure management, AI spotting road damage, or new construction in satellite images. ESA's Copernicus program does a lot of this in Europe.
Agriculture must be huge, too.
Very big. Precision agriculture uses satellite remote sensing for crop monitoring, checking growth, managing water by looking at soil moisture, even predicting pest outbreaks. The USDA collaborates a lot on this.
And the really big global challenges. Climate change, disasters.
Space data processed on the ground is vital there. tracking temperature changes, extreme weather, deforestation, illegal logging, glacier melt, sea level rise. NASA and ESA climate satellites provide the core data for climate science.
And disaster warnings, faster alerts.
Yes, satellites can detect tiny ground movements before earthquakes, track storms accurately, predict flood zones. NASA and Google use AI on satellite data to build better prediction models, helping first responders deploy resources more effectively.
It's clearly such a dynamic area. Okay, let's look ahead. The future frontier. What are the key trends driving space data, and what are the big roadblocks, the challenges?
Well, like we said, those LEO constellations are just going to keep growing massively. Low latency, high bandwidth, lower launch costs. They're plugging communication gaps everywhere. Remote land, oceans, airspace. About 70% of new sats are for comms.
And Starlink is the poster child for that.
For sure. It's providing internet globally. 5,200 millipedes, low latency. Maybe not faster than 5G in cities, but transformative for places with nothing. Look at its impact in Ukraine. Vital comms for military, medical, government. Really shows the power.
Beyond LEOs, how's AI continuing to weave itself into space operations? Manufacturing, safety.
AI is everywhere. In manufacturing, better quality control, finding flaws, flight safety critical for collision avoidance, dodging space debris autonomously.
Which is a huge problem you mentioned.
A massive growing problem. AI also boosts operational security, preventing hacking, managing radio frequencies dynamically, monitoring cyber threats, and making remote sensing satellites smarter, telling them not to waste time imaging clouds, processing data on board.
What about mining asteroids or the moon? Is that getting closer to reality?
It's moving that way, slowly, attracting investment. The idea is to use resources in space, maybe reducing mining on Earth, but the challenges are immense.
The distances alone.
Huge. A 40-minute command leg to Mars means robots need high autonomy. China's developing a prototype six-legged mining bot for microgravity. Still early days, but people are working on it.
And space tourism. Is that going to be more than just billionaire joyrides?
Still very expensive, but demand is growing. Projections suggest it might become, let's say, more common by 2030. Still very niche, but expanding beyond just suborbital hops.
Like actual hotels in orbit.
Concepts exist. There's one plan for maybe 2027 shaped like a Ferris wheel for artificial gravity, holding maybe 280 guests.
And the price tag?
Around $5 million for a few days, so yeah, still pretty exclusive.
What about the really big goals?
Yeah.
Moon bases, Mars missions. Are we actually getting there?
That's the goal of NASA's Artemis program, sustained human presence on the moon as a stepping stone to Mars. Artemis 1, the uncrewed test in 2022, went well.
And the next human landing is planned.
Artemis 3, aiming for mid-2027, plans to land the first woman and first person of color on the moon. Huge milestone. And the discovery of water ice on the moon.
That was game-changing, wasn't it?
Absolutely. Confirmed by India's Chandrayaan-1 in 2008, it means potential life support, water, oxygen, and rocket fuel production on the moon. Makes long-term bases and even launching Mars missions from there much more feasible.
Incredible potential. But let's talk challenges. What are the big hurdles? Cost is still huge, presumably?
Cost is always a factor. Traditional launches cost fortunes. Long missions need vast fuel. But reusable rockets like SpaceX's have drastically cut launch costs. And things like solar sails offer fuel-free propulsion for some missions.
What about just the risk of things going wrong, launch failures?
Still inherent risks. Rockets go off course, engines fail, it's complex. Better autonomous navigation, 3D printing stronger, lighter parts, these help mitigate, but the risk is always there.
And space debris, you keep mentioning it. How bad is it?
It's genuinely alarming. Tens of thousands of trackable objects, millions of smaller untrackable bits, old satellites, rocket stages, collision fragments, even tools dropped by astronauts, all moving incredibly fast.
Which leads to that nightmare scenario, Kessler syndrome.
Right, named after Donald Kessler. The idea is a collision creates debris, which causes more collisions, creating more debris, a runaway chain reaction that could make near-Earth orbit unusable for generations. It really highlights the need for cleanup and better management, urgently.
And then there are the legal and political headaches. Who owns space resources?
That's a huge sticking point. The 1967 Outer Space Treaty says nations can't claim celestial bodies, but it's vague on private companies mining and owning resources.
So different countries have different ideas.
Pretty much. The U.S. and Luxembourg passed laws allowing their companies to own what they extract. Other countries, like Russia, criticize this, saying it violates the treaty spirit, call it space colonization. Lots of friction there.
Are the Artemis Accords helping sort this out?
They're a U.S.-led effort to set norms for peaceful exploration and resource use. But key players like China and Russia haven't signed on. They see it as U.S.-centric, not a true international consensus via the UN. So, more division.
And adding to that, space militarization, is that a real concern?
A very real and growing concern. Increased competition leads to national security worries. Development of anti-satellite weapons, ASATs.
Weapons to shoot down satellites.
Exactly. To disrupt comms, navigation, intelligence. The U.S. tested one in '85. China's 2007 test created loads of debris. Russia's 2021 tested two, even threatening the ISS.
So space is becoming a potential battlefield.
There's definitely a trend towards viewing it that way. The U.S. Space Force, China developing things like robotic arms that could be used offensively. It increases risks, creates more debris, and hinders the cooperation needed for everything else.
And finally, just the business side. Commercial risks must be huge for these space companies.
Absolutely. Huge upfront investments, long timelines for returns. And for markets like tourism or mining, the long-term demand isn't fully proven yet. It's definitely high risk, high reward.
So with all this complexity, potential, challenges, different players, how do government and private companies best fit together? What are their roles?
Government is still critical. They set the rules, policy, oversight, safety standards like the FAA licensing launches. They provide stability.
The framework.
Exactly. And crucial early R&D funding via agencies like NASA, ESA. They invest in the basic science industry builds on, plus promoting international cooperation for big science and investing in education.
And private companies are the innovation engine now, driving down costs.
Largely, yes. They're pushing tech forward, cutting costs dramatically, reusable rockets being the prime example. They're creating new markets, too.
Commercial space stations, satellite internet, tourism.
Right. Building out a sustainable space economy beyond just government contracts. They often take on more market and financial risk in doing so.
Faster, maybe more agile, but riskier.
Generally.
Yeah.
And ultimately, collaboration is key. Leveraging the strengths of both. The NASA SpaceX Commercial Crew Program, sending astronauts to the ISS, is a perfect example of public-private partnership working well.
What a journey. From, spinning hard drives here on Earth to managing data across, well, the solar system practically.
It really highlights how data storage and management are just fundamentally linked to our ability to explore and use space now. Can't have one without the other.
From the tech storing every byte down here, to these incredibly complex systems handling data millions of miles away, data really is the unseen foundation, isn't it? Enabling all these cosmic ambitions.
It truly is, shaping our path forward.
So as we think about this data explosion, our reach into space, here's something for you, our listener, to think about. How will our evolving relationship with data, our ability, our need to secure it, manage it across these huge, often hostile distances, how will that fundamentally reshape human civilization, and maybe even how we see ourselves in the universe?